The last two sections we're going to look at are applications of eigenvalues. We're going to look at 4.8 and 7.2. Both of these will deal with solving differential equations. And if you've had 23, 26, this will all be familiar from Chapter 3 there. It's exactly what we did in Chapter 3, so you already know they're important applications of the eigenvalue problem. So if we have a constant coefficient linear homogeneous system of first-order equations, that is x prime equals ax, where a is a n by n matrix, x is n vector of unknowns, x prime is the derivative of those unknowns. So it's n equations, n first-order equations, and n unknowns, and a is the matrix of constants. Well, you know, in differential equations, they say, let's just try a solution of the form e to the lambda t times a vector of n components, and plug it in and see what the vector and what the lambda have to be for that to work. So you just plug that in. X prime will simply be lambda e to the lambda t times the constant vector u, and then you have a times x, which is e to the lambda tu. And you can factor out the e to the lambda t, which can't be 0, and you have au equals lambda u, which is just eigenvalue problem. So in other words, this will be a solution if lambda is an eigenvalue of a and u is the corresponding eigenvector. And assuming that the matrix A is not defective, in other words, that it has a full set of eigenvectors, which will happen, for example, if they're all distinct eigenvalues, but may happen even if they aren't, unless one of the eigenvalues have geometric multiplicity less than its algebraic multiplicity, then this won't work. It's still possible to solve it, but a slightly different technique. So we'll assume A is not defective. We have a full set of eigenvalues and eigenvectors, and then the e to the lambda 1 t times u1 is a solution, e to the lambda 2 t times u2, where lambda 2 is second eigenvalue, u2 is corresponding eigenvector, and so forth, is a solution. Since linear homogeneous problem, any linear combination is a solution. So that's the general solution, and the constants a1 through an are determined by the initial conditions. So that should all be familiar from 23, 26. Most of the problems you solved there were n equals 2, system of two equations, two unknowns, but this works for arbitrary number of unknowns and equations. For example, the first example they give is a system of three first-order equations. The unknowns are u, v, and w, and A is this matrix of coefficients. We can find the eigenvalues and eigenvectors using the techniques we learned in the previous sections. The three eigenvalues are -1, 1, and 2. And here are the corresponding eigenvectors. Each has a geometric multiplicity 1. There are three distinct eigenvalues. Therefore, the general solution is a1 times e to the first eigenvalue minus 1 times its eigenvector, plus a2 times e to the second eigenvalue, which is 1, t times its eigenvector, and so forth. So that's the general solution. Now, down here, the second example is really the same problem, but now we have initial conditions, as we usually will. So we want to choose the coefficients to satisfy the initial conditions. That's just a question of plugging in t equals 0, which makes all the e to the minus t, e to the t, and e to the 2t makes them all 1. So plugging in t equals 0, u, v, and w is this, and that has to be equal to the initial conditions at t equals 0. So we have three equations, three unknowns. Solve it for a1, a2, and a3, and there are the solutions. Plug it in, and there's your solution for the system which satisfies the initial conditions. Now, you also may remember from 23, 26 that this still works when the eigenvalues and eigenvectors are complex, but then you have to deal with complex arithmetic. So suppose at least some of the eigenvalues of A are complex, and procedure is exactly the same. You find the eigenvalues. For this example, this is the matrix. The eigenvalues of that 2 by 2 matrix are 2 plus and minus I. The eigenvalues, complex eigenvalues, always occur in complex conjugate pairs. The eigenvectors are also conjugate pairs. So we find the 2 eigenvalues and the 2 eigenvectors in the techniques that we learned back in section 4.6, I guess it was. So there's the general solution. So far, no difference except that you have complex numbers for lambda 1 and vectors are complex numbers. Then when you plug in the initial conditions, e to the lambda 1t is still 1 when t is 0. Whether the lambda is complex or real, it's e to the 0, e to the 0 is 1. So you solve for a1 and a2 the same way as before. You plug in t equals 0, and a1 u1 plus a2 u2 has to be equal to the given initial vector 2 and 8. Solve that system. Absolutely nothing different so far, except that the coefficients and the eigenvalues and the eigenvectors are all complex. And in fact, you could actually leave the solution like that. Now that we know what a1 and a2 are, and we know what the eigenvalues and eigenvectors are, that's the solution. But there's something funny here, because the initial problem was there was no complex numbers in the matrix or the initial conditions or anything. So how could the solution be complex? Well, it can't be. It looks like it's complex, but it must not be. The actual solution has got to be real. So it's just a question of simplifying. a1 times u1, we've already done the multiplications there, the scalar times the vector. That's still complex. But now e to the lambda 1t, remember lambda 1 is 2 plus I, so that's e to the 2 plus I t, which is e to the 2t times e to the it. But here's where we use Euler's formula, which says e to the it is cosine of t plus I sine t. If that were e to the 2ti, it would be cosine of 2t plus I sine of 2t. So Euler's formula is key here, because otherwise what in the world is e to the it? So you break this into e to the 2t times e to the it. e to the a plus b is e to the a times e to the b, and put the complex part by itself, the imaginary part by itself. Use Euler's formula for that. And it still looks, the solution still has a bunch of i's in it, but you simplify and behold, the i's disappear. They have to, because the solution has to be real, and there we are. So the eigenvalue problem is not pure mathematics. It has important applications. This is just one of them. Differential equations are most applied area of mathematics, so that's definitely very applied, and eigenvalue problem is useful for solving differential equations. So eigenvalues sounds like a pure mathematics problem, but it has important applications. Your homework, there's a couple of problems in section 4.8 which involve real eigenvalues and eigenvectors, and then a couple of problems in 7.2 where the eigenvalues and eigenvectors are complex.